Hi, everyone. Thank you so much for joining our webinar series. We have a very exciting topic today on the electric powertrain next generation test solutions. My name is Julie Tran, the Digital Marketing Manager at NH Research, and I will be your moderator. Now, before we get started, this presentation is being recorded and will be sent to you after the session is over. Please submit your questions in the toolbox to the right of your screen, and we will try to answer as many questions as we can at the end of the presentation. There is also a quick survey that will pop up in a window at the end of the webinar, and we would really appreciate if you could complete the survey so that we can continue to provide you with high quality content. And now it is my pleasure to introduce our speaker, Ben Jackson. Ben is the Senior Applications Engineer at NHR and has over 10 years of experience in electrical engineering across a variety of industries. He's also highly experienced in the electrification of automotive, aerospace, and grid-tied applications. Previously, he worked at JPL as a systems engineer, and on the weekends, he enjoys to barbecue. Ben is an incredible resource at NHR, and he has been instrumental in providing support and consultation to our customers. So it is with our great pleasure to have him here to share his knowledge and experience with you today. So please feel free to submit your questions in the toolbox to the right of the screen, and we'll get to them at the end. With that, Ben, I will be handing it over to you.
All right, well, thank you very much for that introduction, Julie. And again, thank you very much, everyone, for joining today's presentation on electric powertrain test solutions. So for today's agenda, there's a host of topics that we're going to cover to not only introduce who NH Research is for those that aren't familiar, but also paint a picture for existing and future trends in electric powertrain testing, some of the key challenges associated with it, along with fundamentals in battery emulation as it pertains to electric powertrain testing, and how these challenges and fundamentals come together to form a solution for today's and tomorrow's test needs. So to start off, who is NH Research and what do we do? NH Research is a privately and veteran-owned business with over 50 years of experience in the test and measurement market, and in the last 15 years or so has made a big push into the renewable energy market with applications such as electric vehicles and energy storage. These applications also span many different sectors, as we see the electric growth expanding into the industrial, commercial, defense, and others. And some of these key points that you will hear throughout this presentation are the ones listed below. And these make up the ethos of NH Research. So we design our instruments to be best-in-class performance, user-friendly, easy to use, create modular and scalable solutions to fit today's and tomorrow's test needs, reduce testing time through increasing test efficiencies, improve safety, and increase instrument energy usage. So speaking a little to a few points made in the last slide, NH Research makes a host of DC and AC instruments designed to tackle many different applications to, of course, include electric powertrain testing, but also many others. NH Research has instruments for not only emulating batteries, which we're going to be going over later in the slides today, but instruments that can cycle batteries at the module and pack level, are bi-directional for both AC and DC, AC grid simulators, AC and DC loads and sources, as well as complete power supply test systems. So there really is a wide range of applications that NH Research can tackle, and combined with our drive to produce the highest performance instruments, really a great tool for today's and tomorrow's testing needs, where performance requirements are going higher and higher. So that's who NH Research is in a nutshell. And now we're going to jump into trends that we are seeing in electric vehicle powertrain testing, which has helped us form a cohesive suite of instruments to tackle this testing. So as I'm sure everyone is aware and is evident just by going outside and seeing all the electric cars, there's a huge demand and growth in electric vehicles. And where this is going is up and up, where by 2040 is expected that about 57% of all passenger vehicles sales will be electric. There are a few factors in this growth, such as fuel savings, reducing emissions, and convenience to the end user, but also government mandates, such as the one for the Port of Long Beach in California, that is requiring all vehicles to be zero emission. Now, with a huge growth in electric vehicle sales, this of course translates into a huge growth in the need for the subcomponents that make them up, such as electric powertrains, the topic of today's discussion. Now, with one thing I want to point out, and that I'll be mentioning throughout the presentation, is that electric vehicles do not pertain to just the automotive industry. It covers any vehicle to include aerospace, where we are also seeing a huge growth in electric flight. Just as in electric vehicles, you have a battery, inverter, and motor, you have the same in aerospace. They may look different, but they perform the same basic function. So this slide here, this is an interesting slide, and I like it because it does a great job in showing the evolution of the electric vehicle, which can be extrapolated to the increasing demands for power and performance from their electric powertrains. We can see that there is an obvious upward trend in the performance and capabilities of electric vehicles, where new systems are operating at a much higher voltage and power capability. Where electric vehicles used to have much smaller 20, 60 kilowatt hour packs, they are now closing in on 200 kilowatt hours and more. So this increase in power requirements is directly affecting the requirements on testing, as in new instruments and systems need to be made to properly test them. Additionally, it is clear that the power requirements are continuing to climb. So selecting an instrument that is modular and can expand to the future requirements is also very important. So now that we've discussed kind of that upward trend in electric powertrain testing, it's important to understand some of the challenges faced when testing them. And these challenges are what will drive the instrument selection and ultimately that test solution. So we have broken down some of the common challenges faced when testing electrical powertrains into 6 topics. The first is cost, followed by testing time, real-world simulation, complexity, varying requirements, and safety. Additionally, throughout the next few slides, I'll explain how NH Research has tackled them and the resulting solutions. So starting off with costs, there are obviously a number of things to look for here, as these electric powertrain systems can be quite large. You have development time costs, facility costs, scalability for future project costs, and more. But these all add up and are a challenge when setting up an electric powertrain test system. Choosing instruments that can alleviate these or minimize them is a good way to reduce these costs, and we'll be discussing this today as well. As I'm sure many here are aware, one of the longest lead times is that of the software development cycles. This, coupled with setting up instruments and hardware, can be very time-consuming, lasting months, potentially even longer. And it's for this reason that NH Research offers a full suite of programming options with their instruments, along with sample programs for various software to include LabVIEW and Python. This, along with customer support, ensures that your test setup can proceed as quickly as possible. As discussed earlier, performance requirements are increasing, and as such, selecting an instrument that can fully test the system to these increasing powers and speeds is essential. Having an inverter, for example, that can demand full current in a few milliseconds means that you need an instrument that can supply that inverter in at least that fast. If not, you are missing corner cases and potentially unseen issues can slip by. So here in the next few slides, we'll go over the specs of a few of the NH Research instruments and how they handle this. Electric powertrain testing can also be complex with many different instruments involved. To reduce this, selecting instruments that reduce the total instrument count as well as introduce a more user-friendly interface help to minimize this complexity. So it wasn't too long ago where test systems utilized separate DC sources and separate DC loads to accomplish what can now be done in a single instrument. And requirements ultimately change. From the graph shown earlier, what is needed now will more than likely be too little for what is needed in the future. This means that whatever solution is chosen for the current requirement should have that capability to be scaled up in the future. And we're going to go into this later as well on how NH Research approaches this with their modular systems. Safety is, of course, a huge concern in electric powertrain testing. There is a lot of power present, and with actual batteries, this gets even more dangerous. So this is a very big point when looking into battery emulation that we're going to be going over in the next few slides as well. So we've now covered some of those challenges of powertrain testing. The next thing that I want to cover is not only what is battery emulation, but why it should be considered over a real battery or DC source as some of the key characteristics to look for in battery emulator. So to start off, what is a battery? Now, I'm not going to go into great detail here, as many here know the detail of what makes up a battery. But what I do want to do is draw a connection between what the general makeup of a battery is and how it relates to a battery emulator and why this is so important. So it can be a pretty complex question, but we're going to just keep it pretty simple and straightforward here. Ultimately, a battery is an electrochemical device that converts chemical energy into electrical energy. And as such, there are a number of different chemistries, such as nickel metal hydride, lead acid, lithium, all with their own pros and cons. Some have higher power density, and some do better or worse in inclement weather as examples. But a commonality between these chemistries is their construction. They will have a positive electrode, negative electrode, and some form of electrolyte in the middle. Now, given that basic description, we can say that a battery kind of looks like this, where electrons move from the positive electrode to the negative electrode through an electrolyte solution. Now, this electrolyte, combined with some other mechanical resistances, creates a restriction of electron flow in the battery, and different chemistries will have different restrictions. These restrictions can be expressed electrically as a resistance as shown here. And taking it one step further, here we can see a basic electrical model of a battery where we have our open circuit voltage, that resistance, and the resulting output voltage of the battery measured at its terminals. So in order to properly model this with a battery emulator, you need to have an instrument that can at least simulate this model. And that's where the NH Research 9200 and 9300 models, which we'll go into detail later, achieve this by providing that voltage set point along with a programmable series resistance, allowing for very accurate battery modeling. So when current is demanded from a battery, the battery, providing it is a good battery, and that's a whole other topic in amongst itself, gives the current, but there's a resulting drop in its voltage in relation to its internal resistance, as shown here. And here we can see that when the current hits, the voltage drops, and as soon as the current is released, that voltage pops back up. This ability is what is required in a battery emulator, as without it, you cannot fully test the performance of a battery. As shown below as well, this behavior is modeled by Ohm's law, where the voltage drop or increase is determined by that resistance and current product. This is also a good time to talk about the difference of a battery emulator and a traditional DC source. So, why not use just a traditional DC source instead of a battery emulator? There are definitely a few key differentiators here that are worth noting. The first is that a traditional DC source does not appreciate back EMF that much. Back EMF is where a motor essentially turns into a generator and decelerates, and this energy needs to go somewhere, which is typically back to the source. Some more advanced DC sources may be able to accept some back EMF, but it's a small percentage of the total power and can cause permanent damage, resulting in system downtime and loss in productivity, as well as bring up additional safety concerns. DC sources typically also have a lot of output capacitance, as their primary role or task is to provide a rock solid voltage that is very stable. That's great for applications where you need your voltage to stay in the exact same place all the time. But as was shown in the previous slide, in a battery, that voltage moves around as a result of that resistance and current. Additionally, this capacitance, and for a few other factors, results in DC sources traditionally having very slow current and voltage rise and fall times in the orders of tens, hundreds, or even thousands of milliseconds. There's a slide coming up to show this specifically, but the advancements in electric powertrains and the increase in the performance requirements, faster performance from instrumentation is needed. There are components in an electric powertrain that can push energy in both directions. Motors, for example, a key component in electric powertrains, have inertia, and when decelerating, can push energy back to the source. In a real-world scenario, this would be the battery, and all is good as the battery can accept this energy, but a DC source cannot. This ties back to the back EMF consideration above, but having a battery emulator allows for a seamless bi-directional flow of energy. DC sources also very rarely have a series resistance model. It was shown in the previous slide as well with that battery emulation. Having this series resistance is a very important key aspect in accurate battery emulation. And if using a DC source as a battery emulator, something needs to ultimately be done with the energy in the system that will inevitably come back to the source, whether intentionally or unintentionally. This means, some form of load or way to absorb excess energy. It can mean adding additional fixturing, equipment, or both. And this will, of course, add to the system's complexity where a single battery emulator would resolve this. There are a few reasons to look into using a battery emulator in place of an actual battery as well when testing electric powertrains. So a real battery needs to be charged to a certain point prior to every new test. You can't just snap your fingers and the battery is automatically back at 80% state of charge or wherever it's needed. Real batteries, especially completed packs, which can be costly and large, are not always available. Real batteries deteriorate over time and will not give accurate back-to-back results over time. A real battery has a large safety risk associated with it. When if something goes wrong, there could be a very large fire or worse. And with an actual battery, you are limited to what the battery can do and only what the battery can do. And you cannot overcharge or over-discharge it without risking failure. So you really can't test some of those corner cases. So with those issues noted, a battery emulator doesn't require you to get it to a certain state of charge prior to starting your test. You pretty much, for lack of better words, you can snap your fingers and it will be where you want it to. A battery emulator does not require pulling a fully built battery off the production floor to use for tests, increasing process flow. A battery emulator will have the same results time and time again. A battery emulator has many built-in safety features, along with the fact that it is not full of chemicals that can potentially catch on fire. And a battery emulator can properly test all corner cases to include overcharging and discharging. So as discussed earlier, there are some key considerations to be made when choosing a battery emulator. Ideally, you'll want an instrument that is bidirectional. Batteries, of course, can accept or give energy, and they can do so pretty seamlessly, so you will need an instrument that can do the same. Traditionally, DC sources, which are sometimes used, cannot do this, and sometimes it's the cause of additional failures, as when given back EMF. Output capacitance is a huge consideration, especially when requiring a very fast response time. If you have a battery emulator that has a huge output capacitance and you take current from it, your voltage will be slower to respond to that series resistance component as discussed earlier. Traditional DC sources and some battery emulators have a lot of capacitance on their outputs. NH Research, for example, does not, allowing for very fast transients, but still able to maintain very stable voltage regulation. A battery emulator needs to have that programmable series resistance. Without it, you essentially just have a DC source and a DC load that's bidirectional. Having the series resistance allows you to model that chemical and mechanical resistance that makes up that battery. NH Research utilizes a programmable series resistance that allows that instrument to dynamically respond to the UT at hardware speed, requiring no further input. Additionally, NH Research has a true bidirectional battery mode, meaning that its output can dynamically source and sink current just as a real battery would. This means that at any given point, you can have multiple devices connected, some taking, some giving current, all at the same time, just as you would expect from a real battery. And a wide operating range is key, as shown earlier, with increasing growth in electrical powertrain demands. A modular solution that can expand with your test needs over time is crucial. So we've covered the trends, challenges, and key considerations of battery emulation for electric powertrain testing. Now we're going to go over the instruments themselves that make this possible and the methods for doing so. As noted in a few of the previous slides, there are some key characteristics to look for when choosing a battery emulator for your powertrain testing, as not all are created equal. Bidirectionality is to better emulate a real battery, as well as protect against back EMF, fast voltage and current transients to more accurately represent a real battery's performance, and series resistance being just a few of those. But it's all of the characteristics we've discussed that are brought together to form the 9200 and 9300 DC power modules from NH Research. Just some quick details on these models. The 9200, as seen on the left here, comes in building block sizes of 12 kilowatts up to a maximum power of 252 kilowatts when paralleled. Additionally, that 9200 has a variety of voltage models ranging from 0 to 600 volts DC. And now on the right, we have the 9300, which can be thought of as the big brother to the 9200, where it comes in 100 kilowatt building block sizes up to a maximum power of 2.4 megawatts and 1200 volts DC. And going back to what was discussed earlier, that ability to have a modular battery emulator is important when thinking about future test needs where your power needs may change. It gives a very straightforward upgrade path. For both the 92 and 9300, not only can they be used as battery emulators, as we are discussing primarily in this presentation, but they can also be used as a DC load or as a DC source. So there's a lot of flexibility in operation. Additionally, both are regenerative, meaning that up to 95% of the energy can be saved and not burned off as heat. Another thing that I want to mention here as well, which is something that is a little hard to describe, but both important and something that I'm sure many here have seen or heard rather, is the audible noise associated with larger power instruments. Especially in environments where you will have people working next to or in close proximity to the instrument, the audible noise is a huge factor that is sometimes not looked at until after the fact but can make a much less desirable work environment with that louder noise. And this is why the 92 and 9300s were designed with that in mind, and at full load and idle are much quieter than other alternatives. So as mentioned earlier, when selecting a battery emulator for powertrain testing, speed and performance are key considerations as new technologies and applications are demanding more and more performance. So to just show you what this looks like real quick so you can visually see the difference, here on the left, we have a typical DC source that are sometimes used in these applications. And you can see that it took about 20 milliseconds to get to the desired current. And this is very typical, as you usually have a lot of that output capacitance that we're talking about to manage their voltage stability. This, however, translates into more time to change. This particular current set point was 200 amps, by the way. So in comparison, here we can see the same current, 200 amps, but with the NH Research 9200. And you can see the increase in speed. And again, it's the need for this performance in modern applications where the hardware, the components that make up an electric powertrain, require this. In addition to performance, ease of use is also very important. Having the best tool in the world and not knowing how to use it, or it being so difficult to understand, makes it pretty useless. So having an instrument that can quickly and easily make setting changes is a great thing and are integrated into the design of the 92 and 9300. To turn either into a battery, for example, it's 3 steps and you're ready to go. You turn on the output there in the lower left-hand corner. You're going to then select battery, and then you're going to select the parameters that you want to enter. And that's it. It's that easy. So we also spoke about modularity and how it allows for growing test needs. And with this slide, I wanted to show how that looks. So let's say that you have a powertrain test that requires 200 kilowatts of power. You could have two 9300s as shown here. Now, these two 9300s can either be split up to 2 individual 100 kilowatt channels and run independently, or they can be parallel together for a larger single channel. And additionally, as power needs grow or change, you can add on more instruments for more power or split them up into varying sizes as shown here. The idea is maximum flexibility that allows for scalability of your test setup. There are also many different ways to control an instrument, and these methods vary from company to company and application to application. For this reason, in order to give as much control and as many options as possible, NH Research allows multiple ways to control the 92 and 9300. You can always control the instrument directly from the front touch panel. From here, as shown in the previous slide, it's just a few button pushes to get the instrument set up as a battery and you're ready to go. In addition to the front touch panel, there is an included remote software that gives that same interface and programming options, but you can put it on a remote PC. This gives you the flexibility to control the instrument remotely and not have to be directly in front of it. And along with those controls, you have the ability to control the 92 and 9300 in many different third-party softwares. The most common that we see being Python and LabVIEW. And for both of these, there are sample libraries that can guide you through the process of integrating the instrument into your setup. Additionally, any software, as long as it can open a LAN TCP/IP port, it can connect and communicate with the instrument. So even if you have a proprietary software, they can still be used. So up to this point, we've covered the characteristics to look for in a battery emulator for electric powertrain testing, along with the 92 and 9300 DC power modules. Now that we have that, the next step is how these instruments are used in existing and future test systems. The major components tested in electric powertrains are the electric motor, inverter, and battery. As such, a test setup will need to account for all three, And this is done through the following most common methods depending on the application. There is the single-ended, the common, and isolated DC buses. And we're going to go through each one briefly here to explain them. So in the past, and sometimes still used today for various reasons, the method for testing an electric powertrain is unidirectional. This is where you have a DC source driving one side and a DC load on the other side absorbing energy. Here you can see the energy direction as it flows from the source through the inverter, the drive motor, to the generator, and back through an inverter to the load. Traditionally, in cases such as this, a DC source would be used as the energy is unidirectional, but because of that, still susceptible to back EMF. At this point, all of the energy is burned off as heat or mechanical and electrical loss through the system. And this also means that to run a 100 kilowatt test, for example, it's possible that you're going to burn a bit more than that due to the mechanical and electrical inefficiencies of the system. So similar to the previous method, where there are two sides to the system, there are other applications that require just one side, essentially. These are most common in aerospace electric vehicle powertrain testing, but are present in other markets as well, where the load shown here is actually a turbine, a propeller, or some sort of other rotating mass with inertia. In applications like this, a bi-directional battery emulator is used to not only drive that motor, but then also to accept that back EMF that can be seen when the power is removed and that inertia from the load can back drive energy. So a common method for testing automotive electric powertrain testing and others is what's called the common DC bus. As seen here, both sides of the system are fed by a single source. This allows for energy to be recycled inside the system and not burned off as heat as with a traditional DC load. By using a battery emulator as the source, what this also allows is for the energy to go both ways, meaning that you can drive the motor and it can now become a generator and the other way around. And here we can see the energy now flowing in the opposite direction. So some improvements that this method brings to the table when doing electric powertrain testing are the bidirectional power, which enables you to essentially do two tests in one by testing both sides of the system in both directions. Increases the efficiency of the system by reusing the energy, reduces the need for additional equipment such as separate sources and loads, and the combination of the above mentioned items all creating a simpler system that can test more, reducing test time. So the last approach is a combination of the two previous methods. There are advantages to having separate sources and loads, as we will discuss, but you typically have energy waste. So a common DC bus is shown here and earlier, alleviates that energy waste issue and even reduces equipment requirements. But what if you need to isolate both sides of the system? This can be for electrical noise reasons, research reasons, the inverters having different voltage requirements, or to just better calculate energy use throughout the system. For this reason and for others, you can separate both sides of the test system. So using battery emulators for both sides, you'll note that you also still take advantage of the regenerative nature of that 9200 and 9300. So with any of the approaches mentioned above or previous, whether it's single-ended, common, or isolated DC bus, the battery emulator needs to still do its core function, which is to emulate a battery. Otherwise, you just have a DC source and a DC load at best, and you're not fully testing the powertrain. We've also talked about all the characteristics that a battery emulator needs: speed, performance, series resistance, and more. And that's all great, but the proof is in the real-world results that you can actually see. So here we have a test that was run back-to-back. The data on the left is from a 48-volt battery, and the data on the right, an NH Research 9200. And we first ran the test profile using the battery, then simply swapped the power cables to the 9200, set it for 48 volts with some resistance, and repeated. This particular test was connected to a motor through a DC-AC inverter, and the inverter was commanded to perform a particular drive cycle. Currents ranged from a positive 150 amps to minus 80 amps or so, and the results speak for themselves. So the data very closely matches, which is what should be expected with a battery emulator. Looking at the voltage, which are the blue and orange lines, you can see the slight variance as the current is going from positive to negative. And this is the benefit of having that series resistance in a battery emulator, as without it, you would just have a straight constant voltage there. Another thing to note here is the current, which are the green and red lines. Because a battery emulator is bidirectional, you get a seamless transition from negative to positive currents. By comparison, if using a traditional source or load, you can have discontinuities around that zero crossing, not to mention twice the hardware. So we covered quite a few things today on the topic of electric powertrain testing, ranging from trends to key considerations to introducing the 92 and 9300 and common applications. And with all that covered, I wanted to just quickly recap some of the advantages to using battery emulation for powertrain testing and the benefits that can be found in the NHR instrumentation. So bidirectional power is a big plus for electric powertrain testing. It accepts back EMF caused from the motors and loads, as well as in the case of certain setups, reduces the number of instruments required. Performance is key in battery emulation. Without the ability to do fast voltage and current transients along with series resistance, true battery emulation is very difficult, especially as current and future powertrains are demanding more and more performance. Having a wide operating range is also very important. As battery, module, and pack voltages are increasing, so is the power. So having a solution that accounts for this and has the headroom to grow allows for long-term test stability. Going off that last point, flexible and scalable power. The trend in electric powertrains is one of increasing power. Therefore, having that ability to seamlessly increase power as future requirements change is a great way to ensure a test solution longevity and future-proofing. And safety. Safety is a very large concern. Real batteries for electric powertrains are quite large and as such can lead to potential chemical hazards if they fail. Battery emulators protect against this while adding additional built-in safeties. So with that all said, this concludes today's presentation on electric vehicle powertrains. And I want to thank, again, everyone for their time. A quick note, many of the items discussed today can be found online on the NH Research website, and you're free to access. So please feel free to head over there and take a look. In addition to the presentation, we do have another webinar scheduled for June 16th that you're all welcome to join. We will be sending out a registration link shortly for this, and if you don't see it soon, please don't hesitate to reach out to us, and we'll send you that link. We also regularly update our LinkedIn account, where along with our website, you can find up-to-date information on presentations like this and much more. Additionally, you can also reach out to our staff by email or phone, and we'll be happy to assist you in answering your questions you have. Thank you again, everyone. And now I'm going to open it up to any questions. Julie?
Yes, thank you so much for that valuable presentation, Ben. We do have quite a bit of questions coming in. The first question, what are the best ways to handle feedback current?
Gotcha. Okay, yeah, so for handling that feedback current, that back EMF, current going back the other direction is a fairly common thing in electric powertrain testing. You're inherently working with systems that are designed to drive current in the reverse direction. or equipment such as motors that naturally generate current when decelerating, as a result of their inertia. So this is one of the strong selling points to a true bidirectional battery emulator in electric powertrain testing, as they allow for this current reversal where maybe traditional DC sources do not. It can lead you down a path of damaged equipment, production engineering downtime, etc. Additionally, using passive components such as resistors are sometimes used, but only really complicate or increase the test system.
Okay, and the next question, what does testing look like at the charger side? For example, the power delivery to the vehicle.
Gotcha. Okay. There's a couple different there. You have your AC and your DC. We'll focus on the DC side here. So on the charger side of things, there are multiple levels ranging in power, but also something that is increasing with the addition of the new level 3 chargers and larger electric vehicle battery packs. For the level 3 chargers, we're seeing voltages in the 500 to 600 volt range currently, but also with an upward trend as charge times are wanting to be decreased. And for these DC fast charger application, battery emulators are also important for the same reason as they are in electric powertrains. It's all about that accurate battery modeling.
Okay, and do you test fuel cell electric vehicles in the same way?
Good question. Yes, yes we do. So there's one difference. So with battery electric powertrains, the power can inherently go both directions as the battery allows this to happen. With a fuel cell, energy is unidirectional and only goes one way. So that said, you still have the same components that make up the core system, such as the inverters and motors. So from the perspective of source, a battery emulator is still a valid choice of source in the system and brings the same advantages required out of a battery-driven system, to include things like the performance and safety aspect and modularity.
Yeah, thanks. And let's see, what advantages do NHR battery emulators have over the competition?
Interesting question. So there are some key advantages that NH Research brings to the table. Many were mentioned in this presentation, but there are some others as well. Performance is a big one. That's the 92 and 9300's ability to achieve very fast current and voltage transients in both directions, and that both directions is key. Sometimes it's just one or the other. Typically, we see competitors in the orders of magnitude slower. So the ability to fully test current and future systems is key there. Modularity is another area where NH Research has multiple building block sizes ranging from that 12 to 100 kilowatts, and then also going all the way up to 2.4 megawatts, where we're seeing that increasing power trend from that first or second slide I showed. And this scalability is huge when planning for future tests and needs with that ability to easily expand. And then, as I kind of mentioned earlier as well, just to point out again, noise is a big one that not a lot of people notice until after they have their equipment in front of them. The ability to stay under 72 dB at full load and under 60 at idle is huge, and definitely not the norm for other battery emulators.
Thank you. And let's see, are you seeing use cases for testing heavy-duty battery electric vehicles operating in mining, oil, gas, or construction industries?
Yes, absolutely we are. In fact, a good amount of mining equipment is actually electric, and it's been electric for some time. So this is definitely an area that we're also seeing battery emulators used, and then in this market as well, the same growth. They consist of those same components that you find in electric vehicles, whether it's automotive or flight. You have your same motors, inverters, batteries.
Okay, and I'm seeing a few questions about state of charge. Does the battery emulator have models to estimate varying states of charges under different thermal scenarios?
Gotcha. So so the way the 93 and 9200, as they have many built-in measurements, and one of them is the energy or the amp hours, or we give you the kilowatt hours as well. So as you're doing the test, the thing is to think of the 9300 as the instrument. So we will keep track of all the energy. And then what you can then do with that energy is you can then calculate your state of charge. And that's something that we have customers currently using the 93 and the 9200 to do.
Let's see, how much response time of the battery emulator is in comparison to the real battery?
So there's kind of like a couple different ways you can go with that question. So the 92 and 9300 are capable of doing transients. We spec the 9300 as under 2 milliseconds for being able to do those transient events, and the 9200 in under a millisecond. When I actually test it in the lab, I see much faster than that, just as a point of reference. But yeah, so you're looking in those times, those speeds for kind of being able to do those transients.
Okay, what factors change the internal resistance, and does the 9200 and 9300 emulate the resistance in real time?
Gotcha, absolutely. So yeah, there's a number of things that can vary a real battery's resistance. External ambient conditions, the chemistry used, the state of health, state of charge, all those things can play into that. And what the 93 and 9200 do, which is correct, they do it at real time, at hardware speed, is you have the ability to set that resistance, and you also have that ability to dynamically set that resistance. So, you're not just locked into the same, I have one resistance and that's all you get. No, you have the ability to, whereas as you change your state of charge, you can dynamically then change that resistance in the 9200 and 9300 as well. So you can really get a much more accurate kind of, battery model out of it. And that's something that you can do dynamically, as well as, just one time if you wanted to.
Okay, next question. In the common DC bus approach, how much power from the grid is actually used? For example, let's say a 100 kilowatt system.
Sure. So in a common DC bus approach is kind of that slide that I showed earlier, where you have one battery emulator driving both sides of the system. So in that case, the way to think about that is if you have a 100 kilowatt system, meaning your inverter and motor can do 100 kilowatts in either direction, that energy, that 100 kilowatts, will stay there in that system and kind of be recycled there. The energy that is seen at the wall or your facility is going to be the loss of that system, or the efficiency of the 9300. So that would be somewhere in the order of 95% efficiency. So it'd be 5 to 10 kilowatts that you would see on your facility there.
Next question. What types of safety features are implemented to protect NHR from voltage spikes above limits, for example, from chargers or inverters?
Sure. Yeah, there's a host of safety features, and this is kind of another one of the advantages that once you start looking at NH research or some of the alternatives, these things kind of stand out, which is you have, not only do you have the traditional over voltage, over current, over power type settings, you also have built-in pre-charge circuits. To whereas if you're connecting to a battery or something that has potential out there already, the 93 and 9200 will bring up their internal voltage to match that. So what that does is that reduces inrush and also increases the life of things like contactors and relays. So those are all built in. Additionally, there are battery detect voltages and magnitudes built in, where if someone inadvertently reverses the terminal leads, to whereas you're now connected to a battery reverse polarity, the 93 or 9200 will protect themselves as well. So they have that ability to protect against things, events like that as well.
Next question, does this battery emulator have CAN communication for data logging or other controls?
Gotcha. So yeah, all of the communication on the 92 and 9300 directly is done through LAN TCP/IP. NH Research does have additional software and hardware that can control things like CAN bus for that communication.
And let's see, what are the most commonly used methods that you're seeing for electric powertrain testing?
I would say it's in the automotive, it's definitely the common DC bus. We have seen some applications where they split it up, but the common DC bus, I would say, would be the most common there, no pun intended. And for aerospace, we see a lot of that single-ended, where you're just driving to one side. And that just has to do with the fact that in aerospace, you're traditionally just driving things like propellers or turbines, something that has some sort of rotating mass. So you don't have that secondary side. But those are the two most common things we see for the electric powertrain testing.
Next question. Let's see. Are you able to model the entire system, including the motor and inverter control?
Gotcha. So there's kind of a couple different aspects to that question. So the 9300 itself is the battery emulator. When you start getting into controlling other aspects and other components within the system, that's when you get more to a software level approach, which is where, yes, we do have our software, but then additionally, we work with other third-party softwares that we found a lot of commonality between our customer base, things like Python and LabVIEW that are used to achieve that.
Oh, I'm sorry. I'm just looking through the questions here. Let's see. I think we'll take one more. In a battery emulator, how do you best handle the high power feedback current from an inductive load using a power resistor to dump instead of freewheeling the diode?
Gotcha. So, I mean, if I heard that question right, and that's something we see some customers doing where they have essentially on the DC side, they'll put a large power resistor that is designed to just essentially constantly be burning off power for in the event when the inverter or their motor stops, that energy can be absorbed back into that resistor. So we see that, one of the downsides, of course, to that is whatever power is going through that resistor will always be going through that resistor. And if it's on the DC side especially, it will affect your measurements as well as, how much power you can push to the rest of the test setup as well. We've also seen customers do that with that power resistor on the AC side, which alleviates some of the measurement issues on the DC side, but then of course brings up other issues with burning power all the time.
Okay, thank you so much, Ben. So that does conclude our webinar today. Thank you for participating, for all the questions. There are a few questions here that are a little more complex, and we will definitely follow up with you after the webinar. Let's see. Please stay tuned for our next webinar on battery test automation using Enercon. That will be on June 16th at 2 p.m. Eastern Time, and we will be sharing that information with you, as well as the recording and presentation from this session. So after the session is over, you will receive a survey. Please complete it so that we can continue to support your needs. Thank you all so much for your time, and Ben, thank you again for that valuable info.
No worries. Thank you very much, everybody.
Okay, thank you, everyone.